Hello everyone, welcome to the last video of physics mechanics. In this video, you're going to learn about spring motion, which is an interesting topic because it deals with non-constant acceleration, which is not something that we've seen in this course. You'll first learn about the equation for determining the amount of force a spring exerts. Then you'll learn about equations to describe the interesting motion of springs. Let's dive in. In this video, we will be exploring two PhET simulations, which will both be linked down below in the description. The first one will be for us to understand the basics of spring motion. As you can see in this simulation, the springs are vertical, and that means that the force of gravity applies. We can start off by checking natural length. This just means the length of the springs if they're completely at rest and there's no weight hanging under them. We can drag a 100-gram weight under one of the springs, and it seems like that this is going back and forth and it's repeating the same motion over and over again. We can check equilibrium position. This just means if we stop the motion of the spring, this is how long the spring will be. If we have a block with more mass, then the equilibrium position is more far down. If we increase the force of gravity, then both equilibrium positions go down. And if we decrease it, they both go up until eventually they're the same as the natural length. But now let's just explore one of these two springs. So let's verify if it's actually repeating the same motion over and over again. The first thing that we should check is it reaching the same position every single time? We can check the movable line, move it down somewhere like here. So I'm going to drag this over here. So let's see, does it reach this position every single time? As you can see, it does. The second thing that we should check is, does it take the same amount of time to complete each cycle? So let's try to pause this when it's at the bottom. All right, so I'm going to start this timer, and once I hit play, we will time the amount of time it takes for this to return back to this position down here. All right, so it took about 0.81 seconds. So now we can just reset this timer, and then we're going to be timing it again. So we will see if it's once again 0.81 seconds. All right, so it's 0.8, which is very, very close. So it does repeat the same motion every single time. Now, in real life, this will not happen because of something called damping, which causes energy to be lost as heat. And the effect is the block does not reach the same position every single time. However, for this video, we will be ignoring damping. Now we will dive into the second simulation, which will allow us to derive an important law called Hooke's law. Hooke's law allows us to find a relation between the displacement of a spring from its natural length and the force that the spring applies. Keep in mind that in this simulation, the spring is horizontal, which means that there is no force of gravity, and that means that the equilibrium position and natural length are the same. So we can check all of these except applied force. And now let's adjust the applied force such that the displacement is a maximum. So you can see that when the displacement is 0.5 meters, the force applied by the spring is 100 newtons. Now let's adjust the applied force such that we have the displacement. So you can see that when the displacement halves, the spring force also halves. If we have it again, then the spring force halves again. So you might start to see a linear relationship between the spring force and the displacement. If we change it so that we're compressing the spring instead of pulling on it, we will see the same relationship. So right now the displacement is 0.5 in the other direction, and the spring force is 100 newtons in the other direction. If we have the displacement, the spring force halves. If we have it again, it once again halves. All right, and now this spring constant right here is actually the constant of proportionality. You can see that the displacement times the spring constant is always equal to the force. And you might notice that the spring constant has the units newtons over meters. So when you multiply these two, you will end up with newtons. If you adjust the spring constant, you will notice that multiplying the spring constant and the displacement is always going to give you the spring force. All right, so we've established that there is a proportional relationship between displacement and spring force. However, you might have noticed that if you've ever pulled too hard on the spring, you can actually break it. It's not going to go back to its original shape once you release it. Now, if the applied force is that high, then there's no longer a proportional relationship. The rate that the spring force increases is going to get even faster because the spring tries to resist getting broken. So now let's see what happens if we have more than one spring. So let's go to systems and then check all of these except for applied force. All right, and then, so let's set the applied force to 100 newtons, and that means that the spring force is also 100, and you can calculate the total spring constant by dividing 100 by 0.25, and that will give you 400. And you might notice that 400 is equal to 200 plus 200. Now, if we change one of these spring constants, say to 300, then you will notice that 100 divided by 0.2 is 500, which is still the sum of these two. So spring constants are additive. If you have more than one spring, then the overall spring constant is just the sum of the individual spring constants. To see why this is true, each spring applies its own force, and force is additive. And since force and the spring constant are proportional, that means that the spring constant is also additive. Spring motion is an example of simple harmonic motion, which means that the restoring force, in this case the spring force, is proportional to the displacement from the natural length. So we have the equation F equals negative kx, and the negative sign is there because the force acts in the opposite direction of the displacement. Sometimes you won't see the negative sign. In those cases, you're just solving for the magnitude. If the displacement goes too far, then this relation will stop holding. However, we're not going to get into any of that for this video. Another thing to keep in mind is sometimes the displacement will not be in meters because generally it's pretty small. And in those cases, you have to remember to convert to meters. Equilibrium position is the position where the velocity and the net force are zero. So at the equilibrium position, the spring is not moving and stays at rest. For horizontal springs, the equilibrium position is the natural length, assuming there are no outside forces, because at the natural length, the net force is zero. And for vertical springs, the equilibrium position is below the natural length if a weight is attached. So let's take a look at the equilibrium position for a vertical spring. So at the equilibrium position, there will be a spring force acting upward and gravity acting downward. And these two forces need to be equal. We know that the spring force is the spring constant times the displacement. And in this case, we're going to use L for the displacement, which represents the distance between the natural length and the equilibrium position. So K times L is equal to the force of gravity, which is 9.8 times m. And solving, you can get that L is equal to 9.8 m over K. Now we're getting into period, frequency, and amplitude. Period is the number of seconds it takes to complete one cycle. Frequency is the number of cycles completed in 1 second. If you watched video number 6, then these two terms should sound familiar. A new term that we're introducing is amplitude, which is the highest distance from the equilibrium position an oscillating spring reaches. And now from video number 6, you also learned the relation that period is equal to 1 over frequency. Now we're getting into the displacement equation. The displacement from equilibrium position is equal to the amplitude times cosine of 2 pi times time over period. And keep in mind that the angle is in radians. And this is only true if the spring is at its maximum positive displacement at time t equals 0. If you graph displacement versus time, it's going to give a wave that looks something like this. From this graph, you can determine some values. The amplitude is the distance from the x-axis to a crest. A crest is the highest point in the wave, and the wavelength is the distance between two crests, and it's equal to the period. There are also equations for the velocity, acceleration, and period, but you don't need to remember all of them. Here is the equation for the velocity, and here is the equation for the acceleration. You can also get that the acceleration is equal to negative k over m times the displacement, which is a cosine of 2 pi over capital T times lowercase t. This comes from Hooke's law. Now, using the two values that a is equal to, you can get an equation for the period. T equals 2 pi times the square root of m over k. And another form of this is 2 pi times the square root of L over G. Remember that L is the distance between the equilibrium position and the natural length, and G is the acceleration due to gravity. On Earth, it's just 9.8. And now plugging in what T is into the equation for velocity, you can get another equation for the velocity. Now, which one of these equations do you have to remember? Generally, you should remember the displacement equation and the period equations. Whether you remember the equations for the velocity and acceleration is up to you. Normally, high school physics courses would not require you to remember it, but if you want to remember it, then go ahead because it could be useful. Now we are getting into the energy in a spring. There are many types of energy present in a spring. The first is spring elastic energy. This occurs when the spring is distorted from its normal shape. There's also kinetic energy, which occurs when it's moving. Gravitational potential energy occurs for vertical springs because the object hangs above the surface of Earth. And if there's damping, then we have thermal energy. However, we're not going to have any damping in any of our practice problems. The total energy is the sum of these four energies, and remember that the total energy always stays the same. Now we are going to derive the formula for spring elastic energy. We already know from Hooke's law that there is a proportional relationship between force and displacement from natural length. So suppose we want to apply an outside force that gets the spring to a displacement of x, such that once the displacement is x, the velocity becomes 0. In that case, the outside force will need to be the average spring force, which is half of kx. And we know that energy is equal to force times distance. And now the force is 1/2 kx. So now plugging that in, we get that the elastic energy is equal to 1/2 kx squared. So now we're going to get into practice problems. Here is the first practice problem. If you want to give it a try, pause the video here. The solution will come in 3, 2, 1. So we just used the formula for the distance between the natural length and equilibrium position. And be careful of the units. We have 10 centimeters, which is 0.1 meters. And now plugging that in, we can solve for K to get that it is equal to 196 newtons per meter. Here is the second practice problem. The solution will come in 3, 2, 1. We just used the displacement equation, and we plug in all the values that we know to get that the displacement at 7 seconds is negative 20 centimeters. Here is the third practice problem. The solution will come in 3, 2, 1. Ideally, the lowest spring elastic energy would occur at the natural length, which means that the spring elastic energy is 0. However, an oscillating vertical spring is not always going to reach the natural length. If the amplitude is smaller than the distance between the natural length and equilibrium position, then the spring will never reach its natural length. In that case, the lowest spring elastic energy occurs when it is closest to its natural length, which is at the highest point. So spring elastic energy is the lowest either at the natural length or the highest point. It depends. The highest spring elastic energy occurs at the lowest point because that is when the displacement from the natural length is the highest. Kinetic energy is the lowest at the lowest and highest points because at those points, the velocity is 0. It is highest at the equilibrium position because before equilibrium position, the speed is increasing, and after equilibrium position, it's decreasing. The gravitational potential energy is the lowest at the lowest point because that's when it's the closest to the surface of Earth, and it's the highest at its highest point. Here is the fourth practice problem. The solution will come in 3, 2, 1. The first solution is to realize that since energy is always conserved, the spring elastic energy at the amplitude is equal to the kinetic energy at the equilibrium point. So we know the formulas for spring elastic energy and kinetic energy, so we just plug all the values in and be careful to convert 20 centimeters to meters. And solving, you'll get that the velocity is plus minus 1.79 meters per second, and we only need the speed, so it is positive. The second solution is to use the equations for displacement and velocity. So at the equilibrium position, d is equal to 0. So cosine of 2 pi lowercase t over capital T is 0, and sine of 2 pi lowercase t over capital T is 1 or negative 1. So now we plug in the values into the velocity equation, and we get that the velocity is plus minus 1.79 meters per second. So the speed is 1.79 meters per second. Here is the fifth practice problem. The solution will come in 3, 2, 1. So we use the formula for period. We're going to use the second part of it since we don't know what the mass and spring constant are. However, we know that the distance between the natural length and equilibrium position is 10 centimeters or 0.1 meters, and the acceleration due to gravity is 9.8 on Earth. So we get that the period is 0.63 seconds. The frequency is 1 over the period, which is 1.58, and the units is hertz. Here's the sixth practice problem. The solution will come in 3, 2, 1. So at equilibrium position, the forces cancel each other out, so the net force is 0. So the force of the left spring is just 200 times x, and the force of the right spring is 80 times 50 centimeters minus x. So now you can solve for x to get that it is equal to approximately 14.29 centimeters. I hope this course was really helpful. If you need to review any content from previous videos, in the description, there's a link to the list of all videos of physics mechanics. And by clicking on that link, you can also access a spreadsheet that shows you the list of content covered in each video, so it will be easy to find the correct video. And while you're at it, also make sure to check out my channel because I have numerous other educational courses and videos that could be helpful. And also make sure to subscribe so you'll be notified about future educational content. Thanks for watching. I'm Jesse Lee, and I hope to see you in my other videos.